Neuroscience, Chapter 3, Segment 2. Alan Hodgkin and Andrew Huxley, who were English neurophysiologists, took a giant axon from a neuron involved in the squid's emergency escape behavior. They knew that microelectrodes could be entered into the axon without greatly altering its properties. They established that action potential is created by the movement of sodium ions into the cell through channels in the membrane. A voltage-gated sodium channel is a tubular membrane-spanning protein, but its central sodium-selective pore is closed. When the cell membrane becomes depolarized to threshold levels, the channel shape changes, opening the pore to allow the sodium ions through. These stay open for less than a millisecond. By the time the membrane potential has approached the sodium equilibrium potential of about plus 40 megavolts. Positive charges inside the nerve cell push potassium ions out, and voltage-gated potassium channels open, increasing permeability to potassium even more, so the resting potential is then restored. If you bombard the axon with the ever greater stimuli, the upper limit to the frequency of action potentials becomes apparent at about 1,200 spikes per second. Applying pairs of stimuli that are spaced closer and closer together reveals a related phenomenon. Beyond a certain point, only the first stimulus is able to elicit an action potential. The axon membrane is said to be refractory to the second stimulus. Refractoriness has two phases. The absolute refractory phase is a brief period immediately following the production of an action potential. No amount of stimulation can induce another action potential because the voltage-gated sodium channels are either still open or unresponsive. The relative refractory phase is a period of reduced sensitivity during which only a very strong stimulation can produce another action potential because potassium ions are still flowing out. The cell is temporarily hyperpolarized after firing an action potential. Relatively few sodium ions need to enter to change the membrane's potential, and potassium ions quickly restore the resting potential. The voltage-gated sodium channels monitor the axon's polarity, and the threshold changes its shape to open the pore, shutting down just a millisecond later. Then it remembers that it was recently opened and refused to open again for a short time. These properties produce and enforce the properties of the action potential. Anything that alters the functioning of neuronal ion channels will affect action potential and behavior. Cell bodies and dendrites have few voltage-gated sodium channels, so they do not conduct action potentials. Once an axon potential starts at the axon hillock, it regenerates itself down the length of the axon. Axon hillock is a specialized membrane located where the axon emerges from the cell body. Box 3.1. Cell membrane repels water because it is made of fatty molecules. For water to pass through the membrane, they have to pass through membrane-spanning ion channels. The smallest change in a channel can lead to serious health problems. Channelopathy is a medical condition in which the form and function of ion channels is altered as a result of mutation of the genes that encode those channels. Sodium channelopathy is associated with seizures and heart disease. Chloride channelopathy is associated with deafness and kidney problems. Action potentials are actively propagated along the axon. Axon potential is regenerated along the length of the axon. It's a spike of depolarizing electrical activity, so it strongly depolarizes the next adjacent axon segment. The depolarization immediately creates a new axon potential which depolarizes the next patch of membrane, which generated another action potential, and it continues all the way down the axon. The axon normally conducts action potentials in only one direction, from the axon hillock towards the axon terminals. It leaves in its wake a stretch of refractory membrane along the axon. The cell body and dendrites cannot produce action potential because their membranes have very few voltage-gated sodium channels. Conduction velocity is the speed at which an action potential is propagated along the length of the axon. This varies with the diameter of the axon. Larger axons will allow the depolarization to spread faster through the interior. The myelin sheath greatly speeds up the conduction. The myelin sheath that encases the axon is interrupted by the nodes of Rath, which are small gaps spaced about every millimeter along the axon. Since the myelin offers resistance to the flow of ionic currents across the membrane, the action potential jumps from node to node, which is called saltatory conduction. The action potential is propagated down the axon, and as the axon splits into many different branches, the action potential is recreated in each axon branch until it reaches the terminal. The electrical signal of the axon potential is converted into a chemical signal as the axon terminal releases another neurotransmitter. A neurotransmitter is a chemical that is released from a presynaptic terminal that series to communicate with the postsynaptic cell. Box 3.2. At electrical synapses or gap junctions, the presynaptic membrane comes closer to the postsynaptic membrane than it does at chemical synapses. At electrical synapses, the facing membranes of the two cells have relatively large channels to allow ions to and from one neuron directly into another. As a consequence, the electrical current that is associated with neuronal activity is one neuron can flow directly across the gap junction to affect the other neuron. Electrical synapses work with no time delay and are frequently found in neural circuits that mediate escape behaviors in invertebrates. Neurotransmitters released into synapses briefly alter the membrane potential of the postsynaptic cell. The changes are called postsynaptic potentials. A neuron is subject to hundreds to thousands of postsynaptic potentials. The potentials determine whether the neuron will reach threshold and generate an action potential. In Figure 3.9, the stimulation of an excitatory presynaptic neuron in red causes it to produce an all or none potential that spreads to the end of the axon, releasing the transmitter. After a delay, the postsynaptic cell in yellow displays a small local depolarization as the sodium channel opens. The postsynaptic membrane depolarization is called an excitatory postsynaptic potential because it pushes the postsynaptic cell a little closer to the threshold for an action potential. If excitatory postsynaptic potentials are elicited by many neurons that converge on the postsynaptic cell, these potentials can produce a depolarization large enough to reach the threshold and trigger an action potential. Postsynaptic depolarization begins half a millisecond after the presynaptic action potentials arrive at the axon terminals. The delay is called a synaptic delay, and it reflects the time needed for the transmitter to be released and diffuse across the synaptic cleft. The action potential of an inhibitory presynaptic neuron in blue looks like that of an excitatory presynaptic neuron. The effect of the postsynaptic side is different. When the inhibitory neuron is stimulated, the postsynaptic effect is an increase of the resting membrane potential. The hyperpolarization moves the cell membrane potential away from the threshold, decreasing the probability that the neuron will fire an action potential. This is called inhibitory postsynaptic potential. The inhibitory postsynaptic potentials result from the opening of channels that permit chloride ions to enter the cell. The chloride ions rush into the cell, making it more negative. Synaptic transmission performs information processing using a neural algebra. Each neuron adds and subtracts the myriad of inputs and receives it from other neurons. Postsynaptic potentials are caused by transmitter chemicals that can either be depolarizing, which is excitatory, or hyperpolarizing, which is inhibitory. When summed, the excitatory and the inhibitory postsynaptic potentials cancel each other out. The resulting sum is also influenced by their distance. Spatial summation is the summation of potentials from different physical locations across the cell body. Temporal summation, the closer the postsynaptic potentials are in time, the greater overlap and the more complete is the summation. Although action potentials are an all or none phenomena, the overall postsynaptic effect is graded in size. The membrane potential at the axon hillock reflects the moment-to-moment integration of all the neuron inputs, which the hillock encodes into an ongoing pattern of action potentials. A vast amount of synaptic inputs arrayed across the dendrites and cell body can induce postsynaptic potentials. The further out an a dendrite of potential is produced, the less effect the potential should have at the axon hillocks, because the potential decreases in amplitude as it passively spreads. Some neurons have a dendritic integration zone featuring voltage-gated ion channels which sum and amplify local postsynaptic potentials, increasing their impact at the axon hillock. Glial cells increase the strength of the postsynaptic potential, overlaying the presynaptic terminal, preventing neurotransmitters from leaking out of the synaptic cleft.